Hey folks, hope everyone's doing okay. This might be one of the last videos that we end up having. I really don't know. I know we got quite a few assignments that are still out, and to be quite honest, I'm getting kind of wore down with this online version of instruction, especially with this particular unit and the last one anyway. There was so much cool crap that we missed out on, and it's so disappointing that we didn't get to see a whole lot of stuff with it, but that's okay. Let's go ahead and get this video done, and then I'll see if I'm going to move on to any of the other topics. There may be one or two other little things go in, but as far as the big math, I think this will probably be the end. The next concept would require a little bit more time to invest in what we have, and I want to kind of get started with the review. Okay, once again, I'm kind of shortening this down, so I'm jumping straight to spectral lines and emission spectras and so on. Those of you who have had college chem, most of this you should already know, but we're just going to go into this in a little bit more detail maybe than what college chem did, or give it a little flavor on the physics side of it, so that you can fully understand some of the things that you may have learned in college chem. All right, so we knew about spectral emission lines way back, before the 1850s. Okay, so basically, an emission spectrum displays the exact wavelengths of light that are emitted from a source. Now, we know by now, or we should know, that if I have a white light for a source, then I will get a continuous emission spectrum, okay? But if we are generating light using hydrogen gas only, or neon, or whatever, we can, neon lights, obviously, we have a bunch of different colors that are emitted from it, but it still produces its own emission spectra. If we're just looking at hydrogen gas here to keep it simple, if we can take all of these lines out of this continuous spectra, what we get is 4 visible wavelengths that are emitted from the hydrogen gas. We can actually see this. Now, if I turn on just a hydrogen lamp, you're just going to be able to see it glow. And it's not going to look that much different to you. It'd be a little bit different of a color than a white light bulb, but you still wouldn't be able to distinguish all of the colors, because it is a mixture of these 4 that your eyes can perceive. Now, there's a lot of other lines, so to speak, on this emission spectra that hydrogen produces, but these are the only 4 that we can actually see. If we were to use a diffraction grating, as we learned about in Unit 6, and we put it up in front of a hydrogen light source, then you would be able to see all of the different wavelengths of the light that are projected from this. Except this one right here is pretty darn close to 400 nanometers. It's very, very, very hard to see, but these are the 3 that I can always see. I can never see this 4th one. All right, so moving on. Balmer in 1885 developed an equation to solve for these 4 emission lines. To be quite honest, at that point, they did not know what they meant. Balmer just knew in his equation that if he used a specific number, then the math worked. And his specific number was actually 3 that he ended up plugging in, anyway, they ended up showing the math correctly with this. Now, Balmer's equation, though, was an absolute nightmare to use. So I'll come back up to this here in a second. Rydberg came along later on and developed a simpler way of looking at this and simplified Balmer's equations, where instead of trying to figure out and use the actual wavelength, he used a concept called wave number, and basically just inversed it. So it's the number of waves occupying a specific length. And Rydberg came up with this equation to solve for the specific wavelengths. Oh, I just realized I said 3 for Balmer, and it's actually 2. So anyway, I'll get back to that. Rydberg used his equations to be able to find the actual wavelength on all of these lines from this Balmer series. Okay, so these first 4 lines on this, and to be able to figure it out. Once again, if you look at this equation, it has a couple of n's in here, and he just knew that if he used this n as a 3, 4, 5, 6, and this one was always 2. Okay, so basically he just knew that one of these n's had to always be 2, and the other one could be 3, 4, 5, or 6. Then he could calculate the value for the wavelengths exactly on those specific emission lines. Okay, so basically what he was solving for was Balmer series, was everything started at 1 point and then went down to 2. Now, they found a couple, as they were able to test a little bit more accurately and use different resources to study this, they were able to find that there were other series as well. Okay, the Lyman series all had n values of 1, and the Paschen series all had n values of 3, and there's others, I forgot what they're all called, but there are several other series where it goes to the 4s and 5s and 6s and so on this. Now, those of you who haven't had college chem, this is where it comes down. All of this information here basically comes down to this. Okay, Bohr model of the atom, 1913. So it wasn't until several years later that Bohr came along and figured out that, wait a second, these numbers actually mean something. These 2s and 1s and 3s and so on. So the Bohr model of the atom was basically created around the fact that electrons do not lose energy as they exist in stationary orbits. Okay, remember, when we were talking about Rutherford's planetary model before, that was one of the big problems with his model of the atom, was that electrons should just continuously lose energy, and which means they should basically crash and burn towards the nucleus. Okay, we know that does not happen. So Bohr came along and solved for the fact that electrons don't lose energy as they exist in their stationary orbits, and there are specific energy levels associated with that. All right, so here's what I did. On Canvas, I placed a derivation of this on the on a piece of paper for you guys to kind of go through and look at. The reason I wanted you to do this is we're going to be getting into these orbitals here in a little bit with the amount of energy that the electrons have. And if we think about an electron just orbiting a nucleus of an atom, the electron's obviously moving, so it has kinetic energy, but it's also at a distance away from the nucleus of the atom, so it also has potential energy, but it's not gravitational potential. The gravitational potential is negligible here. It's the electrostatic potential energy. And if we remember from last year, we didn't talk about it too much, but for an orbiting objects above the Earth or escape velocities, remember we assign 0 at infinity. So really gravitational energies as we work backwards from infinity become negative numbers instead of positive numbers. So when you look at the derivation, I kind of explained that a little bit. But when you do look at the derivation, you're going to see that the first energy level has a value of negative 13.6 electron volts. And then the second energy level is negative 3.4 electron volts for the hydrogen atom. So those are going to be numbers that we're going to see here in just a little bit. So it would definitely help to look through the derivation really quick. It's not a very hard derivation. All right. So anyway, going back to this. Orbits must be specific and discrete. So basically what Bohr did is he quantized the atom. Okay, just like we talked about quantum theory with light, he quantized and made discrete units for which the electrons will orbit. Now, our current model of the atom has taken this a few steps further, and our current quantum model now puts, which is interesting, quantum means making it in discrete units, and our current model uses most probable locations, which treats the electrons as waves. And once again, if we can get to some of that stuff here in the next few days, we might. If not, then it's too bad, because it's pretty interesting. Okay, so anyway, back to this. Electrons can only gain or lose energy from jumping from one orbital to another. So in order for the electron to gain energy, a photon must be absorbed. So if the electron absorbs a photon of a specific energy level or energy amount, it will jump to another specific orbital. Okay? If the electron drops to its ground state or to any other orbital, then a wavelength of light will be emitted from the electron in order for it to lose the energy. Okay? So basically what happens in a light bulb, like a hydrogen gas bulb, we plug it into an electrical source. The electrons in the gas get really energized, and then they start jumping back down to their ground state before they get re-energized. And as they jump down their ground state, they will release a specific wavelength of a photon. Okay, and depends on how energized those particular electrons are, will depend on which wavelength of light is ejected from it. Okay, so that explains then basically what all this does is this explains these four spectral lines that we can see from hydrogen. Okay, as we will see, the second energy level, if the electron transitions from energy level 3 to energy level 2, then it's going through the transition in the Balmer series, and that's going to be the smallest amount of energy of any of the electron or any of the wavelengths that is going to be released from that we can see. So small energy means long wavelength. So that is going to produce your red end of the spectrum. If something drops from level 4 to level 2, then we're going to get the next light that comes off of it, 5 to level 2, and then 6 to level 2. Any electron jumping from level 7 to level 2 is going to be too much energy for our eyes to perceive. The photon is still there, but it's going to be in the ultraviolet region of the spectrum. Okay, so going back to the series then, if we're looking at just the Balmer series, the first 4 lines of the Balmer series are visible, and anything after that is in the ultraviolet region. We get to the Lyman series, and these are all transitions to level 1, so down to the actual ground state that the electron can exist in, the least energetic state for the electron. All of these lines are in the ultraviolet region of the spectrum for hydrogen gas. The Paschen series to level 3, these are all in the infrared region of the spectrum, okay? So we still wouldn't be able to see any of these. We can't see any of these with our unaided eye, and we can't see any of the Balmer transitions other than the first 4. Those are the only 4 that actually are occurring within the visible region of the spectrum, okay? All right, so here's basically what we have. Remember, we're going to set infinity as 0 energy. And notice these are in electron volts, so you should be able to convert these over to joules pretty easy, because all you have to do is just take them times 1.6 to the negative 19th. The first energy level for hydrogen has an energy of 13.6 electron volts. Basically what this means, this is the ionization energy of hydrogen gas. So in order to remove the electron, we're going to have to give the electron 13.6 electron volts of energy in order to ionize that, okay, if it's in the ground state. If it's in a more energetic state, then we don't have to add quite so much energy in order to ionize the gas. The N2 level is 3.4 electron volts, and so on. So for every element, these energy transitions are going to be different. Now, hydrogen is really easy. There's only 1 electron, so that's a pretty simple thing. Another thing I want to make sure we understand. This Rydberg equation, I know in chemistry you guys use it quite a bit. We will use it a little bit, but I don't want you to rely on it, because this only works for hydrogen gas. So if I don't give you this energy transition chart, you cannot use the Rydberg equation, okay? Because it will not work. we can use the Rydberg equation to get all of these values with the wavelengths and energies and so on. This is just another visual of the different transitions. Once again, you can see the different energy levels and states that the electron can exist in as they drop down to state 1, which is the ground state. This is the part of the Lyman series to N1. Balmer series are all the transitions to N2. And once again, you got your red, green, kind of bluish, and then your violet, and then your ultraviolet over here, and then Patchen series, and then the bracket series, and then N5, and so on and so forth. Okay, it just keeps going. All right, I'll solve these things on your on a practice round here probably tomorrow. I'm not going to mess with it right now. There's enough other stuff to look at and do, and you guys have enough assignments. I'm not even going to post another one right now. So anyway, wanted to make sure that I reviewed this with you real quick, but if I ask for the ionization energy, that's going to be the energy needed to remove the electron from the ground state. So for hydrogen, that will be N1, so obviously it's going to take 13.6 electron volts in order to remove that. Okay? Once again, I'll show you guys how to solve for some of these things. I'll write up a little sheet and post it tomorrow night when I get ready to move on for Wednesday, I guess. Days are all running together. Okay? All right, I'm going to shut down this video right now. Hopefully some of that made sense, and I know this topics are all of these topics right now that we're getting into. These are all really challenging, and once again, I got a lot of cool visuals and things like that, and we're missing out on several labs that I would normally do just to be able to explain these, but anyway, kind of the way it is, right? So anyway, I'm going to stop there. Have a good night.